Okay, so we are now at the last module for lecture 2, where we will be introducing a network of perceptrons, right. So now the word network has come in and we will be seeing what a network looks like, and then we will talk about the representation power of such a network of perceptrons, right. So what we are going to do is, we are going to see how do you implement any boolean function, irrespective of whether it is linearly separable or not to begin with, using a network of perceptrons. Although we know that we are using a single perceptron, we cannot build it, right, we cannot implement it. Okay. So now for this discussion, this is more like an illustrative proof, right. So we are going to not have a proof which has like a set of mathematical steps. It will just be like we will prove something by constructing a network itself, right. So let's for this discussion, right, we will assume that true is equal to +1 and false equal to -1, as opposed to 0 and 1 that we have been using so far, right. And we will consider the case of 2 inputs, okay, and we will have 4 perceptrons. So since I am going to have a network of perceptrons, it is clear that I am going to have more than one perceptron. So now I am going to start with 4 perceptrons, right, and each input is connected to all the 4 perceptrons, okay, with specific weights, and the red weights are -1 and the blue weights are +1, okay. Why so? All that we are not considering right now. It is just that you have 2 inputs, 4 perceptrons, every input is connected to every perceptron by specific weights. Some weights are -1, some weights are +1, right, and then the bias or W naught is equal to -2, okay. So W naught is -2. So what is the perceptron rule? W naught plus the weighted sum of the inputs should be greater than 0 for it to be 1. So what does that mean? If W naught is -2, then the perceptron will fire only if the weighted sum of the inputs is greater than 2, because then you will have -2 plus a quantity which is greater than 2. So that quantity would be greater than 0, greater than equal to 0, and then the perceptron will fire, right. So it means that the weighted sum of the inputs should be greater than equal to 2. So this is all I have done, this match fixing, right. There is, I have like hard coded everything so far, okay. Then I have one more perceptron, which is my output perceptron. What does that mean? That the output of this perceptron will be the output of the network. And if I want to implement a function, if I say I want to implement the XOR function using this network, that means that for a given input 0 0 0 1 1 0 1 1, the output of this green perceptron should match the truth table of the XOR function. Then I would say that I have implemented the XOR function. That is what I want. And now each of these perceptrons, the red perceptrons, is connected to the green perceptron using a weight, and I am going to call those weights as W1, W2, W3, W4, okay, and then the output is Y. This is all the setup that I have. Now why this setup, where am I headed, all that is not clear, but you cannot stop me from having this setup. All this is straightforward, right? I have 2 inputs, 4 perceptrons and then one output perceptron. For the first set of red perceptrons, I have hard coded the weights, okay. Now I am going to introduce some terminology, and this terminology is going to stay with us for the rest of the course, right. So this network contains 3 layers. The layer containing the inputs is called the input layer. So x1, x2 is the input layer. Then the layer containing the 4 perceptrons is called the hidden layer, right, because this is between the input and the output. So it is not exposed to the outer world. I have something happening here which the outer world does not care about. I do not care about what is the output of these red perceptrons. I care about the output of the the green perceptron. This is a hidden layer, and the output neuron is what is forming the output layer, right. So I have 3 layers: input layer, hidden layer and output layer, right. And the outputs of the 4 perceptrons in the hidden layer, I am denoting them as H1, H2, H3, H4. The output of the final layer, I am denoting it as Y, and the red and blue edges are called the layer 1 weights, and W1, W2, W3, W4 are called layer 2 weights, okay. So there are 2 layers, one hidden layer, one output layer, and I am not counting the input layer because it is there, right. So this layer 1 weights are called the red and blue edges are the layer 1 weights, and W1, W2, W3, 4 are the layer 2 weights, okay. This is all definition, all terminology. Now is the interesting part. I am going to claim that this network can be used to implement any boolean function, whether that function is linearly separable or not. What does that mean? It means, what I am trying to say is that I have this generic template which has now 4 weights W1, W2, W3, W4. Everything else in the network has been hard coded, right. The only 4 variables are W1, W2, W3, 4. Using this template, I am claiming that I can implement any of those 16 Boolean functions which I had shown, including the XOR and the not of XOR function, right, which are not linearly separable to begin with, right. So what does that mean is that I can learn specific values of W1, W2, W3, W4 for each of these 16 Boolean functions, and these might be different values for the different functions, such that when I plug in those values and now I start feeding 0, 0, 0, 1, 1, 0, 1, 1, then my output would be the desired output as per the truth value of that function. That's the claim I am making, and this looks like an astonishing claim, right? Because I know that some of these functions are not linearly separable. That's one reason why this is an astonishing claim, because I am claiming that even non-linearly separable Boolean functions I can establish. The other reason why this is an astonishing claim is that this is just like a single template. I am not having like a separate network or separate configuration for different Boolean functions. I have the same configuration. The only thing that is changing is the weights of W1, W2, W3, W4. If I change those values, then I can implement any Boolean function, right? So this may look like an astonishing claim, but it's not really if you really understand what is going on. So what is going on here? Let's try to understand that, right? So each perceptron in the middle layer fires only for a specific input. Let's see why that happens, right? So as I said, the red weights are -1, -1, okay. Now if the input is -1, -1, remember that 0 is -1 here. So these are the 4 inputs that are possible: -1, 1, 1, -1 and 1, 1. Right? These are the 4 inputs that fire. Now if the input is -1, -1, what will happen? -1 into -1 will be 1, -1 into -1 will be 1, so the sum will be 2. So the weighted sum would be greater than or equal to 0, -2 plus 2, hence this perceptron will fire, okay. And now I will show that this perceptron will not fire for any of the other 3 inputs, right. If this is the input, then you have -1 into -1, which is 1, 1 into -1, which is -1. So 1 minus 1 will become 0, and plus the bias will become -2, which is less than 0. So this perceptron will not fire. Similarly, you can see that for these 2 inputs, this perceptron will not fire. So this specific perceptron is only going to fire for this input, because that's how I have configured the weights. That's why I had this 2 red edges there, -1, -1, because with that set of weights, the only way this perceptron can fire is for the input -1, -1. Is that okay? Right? Similarly, you can now go back and check, right, that the second perceptron, the first perceptron will only fire for -1, -1. With the same argument, the second perceptron will only fire for -1, 1. I'll show you how. So this is -1, this is 1. So if your input is -1, -1, so you'll get -1 into 1 is 1, 1 into 1 is 1. So 1 plus 1 is 2, plus the bias is -2. So this quantity would be greater than or equal to 0, hence the perceptron will fire. And you can check for any of the other 3 inputs, it will not fire. Similarly, the third perceptron will only fire for 1, -1. The fourth perceptron will only fire for 1, 1. Okay. So each perceptron is like kind of specializing for a specific input, and it will only fire for that input. Now the question is, so what, right? I mean, how does this show that it can handle any function? Right? So we need to go back to the table that we had and the algebra or the calculations that were happening there, right? So let's see what is happening here. So if you have the XOR function, now XOR function is the troublesome function because it's not a linearly separable function. So let's see what will happen in this network for the XOR function. So when you have the input as 0, 0, now when I say 0, 0, assume -1, -1, the XOR truth table says that the output should be 0, right? Now we know that H1, H2, H3, H4, the H1 will take on the value 1, everything else would be 0. So if I look at summation Wi, Hi, it will just be W1, correct? Right, it will be W1 into H1 plus W2 into H2 and so on. So H2, H3, H4 are 0, so the last 3 terms will be 0 and the first term, which is W1, will remain. Now if the input is 1, 0, then for the XOR truth table I know that the output should be 1. Now my H1, H2, H3, H4 will take on these values and my output would be only W2, because my output is the summation of Wi, Hi. Now 3 terms will go to 0 there, only the W2 into H2 term will remain, which will just be W2 because H2 is 1. Is that okay? Now for the next input W3, the next input W4, right? Now if I go back to my conditions, what are the conditions that I want. So if I want this to behave like the XOR function, then W1 should be less than W0, right. In that case it will not fire, and hence it will be the same as the truth table of the XOR function. Let me just clear some things. So W1 should be less than W0. If that is the case, then it will not fire and I will get the output, the desired output. Is that okay? So this is -1, right? Okay. This is the truth table. Yeah, the truth table has a problem. So this should have been 0, 1, and this should have been 1, 0. Okay, is all this fine now? Okay. So now for this to behave, so this is the aggregated that I get, right? Now what is my y? If the aggregation is less than W0, then it will be 0. If it's greater than W0, it will be 1, right? So now for this to behave like the XOR function, W1 should be less than W0, W2 should be greater than equal to W0, W3 should be greater than equal to W0, W4 should be less than W0. There is nothing new I have done here, we did the same exercise earlier on, right? But now what is the difference? Do I have any contradictions here? I do not have any contradictions here. Earlier when I had the XOR function with a single perceptron, I had contradictions in these inequalities. Now I do not have any contradictions because I have 4 weights W1, W2, W3, W4. I have 4 independent conditions that they need to satisfy. There is no condition that is contradicting, right? And why is this happening? Because this is how I have designed it. Every neuron here, every perceptron here is firing for a specific input, and hence that is leading to a condition on a specific weight. And 2 weights are not interacting with each other in any condition, hence there are no contradictions that are happening here, right. So the network has been designed in a way such that you have 4 possible inputs and you have now these 4 possible weights. So you have these 4 degrees of freedom. So each weight can adjust to satisfy a given input. Does that make sense, right? So that's what is happening here. I have come up with conditions which are not overlapping or contradicting with each other. So hence, irrespective of what the Boolean function is, now you can go and try the same thing for any other Boolean function. You can go and figure out the conditions and the same thing will happen. You will have only W1 in one condition, W2 in another condition, W3 in another condition, W4 in another condition, right? And hence you can always satisfy this by adjusting the W1 to W4 in a particular manner. Is that okay? Fine. So that's why, since there are no conditions, each input is being handled by a specific perceptron, hence you can implement any Boolean function in this case, right. And not just the XOR function, as I said, you can implement any of the 16 Boolean functions. So for each Boolean function you will get a different set of conditions for W1, W2, W3, W4, and you can find some values of W1, W2, W3, W4 which will satisfy that particular Boolean function, right. So you can go back and try this out, okay. Now what if we have more than 3 inputs? Can you think of the same template now and adapt it for the case of more than 3 inputs? The same idea will repeat. You will have x1, x2, x3. Now instead of 4 perceptrons in the middle layer, you will have 8. Why? Because there are 8 possible inputs now, 0, 0, 0 up to 1, 1, 1. So each of these perceptrons, you will adjust these red and blue weights in a way that for each perceptron only fires for a specific input, right. The first perceptron will fire when it's 0, 0, 0, second will fire when it's 0, 0, 1 and so on, right. So now each perceptron again fires for a specific input. Each perceptron interacts with the green perceptron by one of the weights W1 to W8. So again when you write down the conditions in the truth table, you will have conditions like W1 has a specific condition, W2 has a specific condition. None of these conditions will contradict, none of the weights will interact with each other in any of these conditions. So you can find the values of W1 to W8 such that all your 8 inequalities are satisfied for any of the Boolean functions, right. So again you will be able to implement all the Boolean functions which are possible, okay, fine. So that's the same template that you have used. So what if we have n inputs, right, more than 3 inputs which is n inputs, okay. So then how many perceptrons will you need in the middle layer? 2 to the power n, right. So when you had 2 inputs you needed 4, when you had 3 inputs you had 8. So when you have n inputs there are 2 raised to n possible values that the inputs can take, right. So, each perceptron will handle one of these specific inputs, and then you will have 2 raised to n weights in the output layer, and you could adjust them, right.
The bias will also be minus n?
Yeah, bias will stay the same, minus n, right. You could hand code the bias, right. So, now what does this theorem say now? Any Boolean function of n inputs can be represented exactly by a network of perceptrons containing one hidden layer with 2 raised to n perceptrons and one output layer containing one perceptron. How do you prove this? We have already proved it, right. We proved it by construction. I gave you the network, I gave you the template. If you have n inputs, you will have 2 raised to n perceptrons. Each perceptron will cater to a specific input. Then you will have these 2 raised to n weights in the output layer. Each weight will have a specific condition which you can satisfy because there will be no contradicting conditions, right. So, note that this network which has 2 raised to n plus 1 perceptrons, 2 raised to n in the middle layer and 1 in the output layer, is not necessary but sufficient. All this is saying that if you have 2 raised to n plus 1, you can implement it. But we have already seen that the AND function can be implemented by a single perceptron. So, you do not really need 2 raised to n plus 1 perceptrons, right. And the catch here is, of course, while this theorem looks interesting, is that as n increases, even if it becomes 10, 20, 100 also, it becomes unmanageable, right, because you will have 2 raised to 100 neurons, which is obviously going to be very large, right. So, this increases exponentially. So, we will have to see a way of coming back from here, right, coming back from this exponential situation. But for now, we are happy that we can, even if there are Boolean functions which are not linearly separable, which a single perceptron cannot handle, we can have a network of perceptrons which can handle that. How to make this network a bit more compact is a question for later, but now we know that we can handle with a network of perceptrons. So, again, while we have proved this, why do we care about Boolean functions? Right? So, let us try to relate this to a real world example, the same example of predicting movies, right. So, this is how the example plays out, that you have certain features as you call it. So, these were, is actor Matt Damon, is the genre thriller, is the director Christopher Nolan, and so on, okay, all these factors, and these are the labels that you are giving, and these are all your past movie examples. There are some examples which I am calling the positive examples because their label was 1, and some examples which I am calling the negative examples, which for my labels are 0. And as we had argued earlier, for most real world examples, the data will not be linearly separable. That means you cannot draw a line such that all your positive examples lie on one side, all your negative examples lie on the other side, right. So, what I have shown you here is a Boolean function, right. These are all Boolean outputs, and I have taken all inputs as Boolean, right. So, this is a Boolean function, and in reality, in real world examples, this will not be linearly separable. And this is a very real world example, right. You have some n Boolean decision factors based on which you are taking a Boolean decision or a binary decision, and now you want to be able to learn that. What this theorem is saying is that you can come up with a network of perceptrons which will exactly implement this function. What does that mean is that whatever your truth table looks like, and this is what your truth table is looking like, right. You can come up with a perceptron network of perceptrons so that it will exactly be able to implement this Boolean. So, right, this theorem says that you can apply this in real world examples. The catch, of course, is that you will need an exponential number of neurons, perceptrons, and we will have to get back from that situation, right. But for now, we are happy in knowing that it can be done, right. Now, how to do it more efficiently is a question for later, right. So, that is what this is saying, as the same thing which has been written on the slides, you can read it later on, okay. So, what is the story so far? The networks of the form that we just saw are called multi-layer perceptrons, or MLPs in short. You would have heard about this in several contexts. The more appropriate terminology is actually multi-layered network of perceptrons. Why? Because you have perceptrons, there is a network of perceptrons, and there are many layers, so it is a multi-layered network of perceptrons. Multi-layer perceptron does not make sense. Right? There is a single perceptron, it is not multi-layer. It is a multi-layered network of perceptrons, but more commonly MLP is the common terminology that is used, right. The theorem we just saw gives us the representation power of a MLP. What does that mean? What kind of functions can it represent? It says that it can represent any Boolean function. So, that is the representation power with a single hidden layer, right. Yeah, so that is all that we have for today. So, we have been talking about the perceptrons. We went a bit deeper into the perceptron learning algorithm. We saw that it actually converges. Then we saw that a perceptron has a limitation. It cannot deal with functions which are not linearly separable. Then we made a case that in many real world examples, functions would not be linearly separable. So, we need to deal with that situation. And we dealt with that situation with a network of perceptrons. We are still not completely happy because we have an exponential number of perceptrons, but we are able to map this again to a real world problem where you are given some data and that data may not be linearly separable. But now given this template, you can come up with a network of perceptrons and learn the weights Wi's in your network such that it will give you perfect separation on the input data, right. Now from here we need to go a bit ahead and see how can we get rid of this exponential number of neurons, and then also go a bit ahead and see if we can do something about this linear decision boundary. So, these are things that we will deal with in the next lecture. Thank you.